I suggest we continue. And so I now go to the second topic, which is orbital integrals. And characters. So in the beginning, I promised that there would be a relation between geometric and algebraic scenes. And up to now, we were doing some differential geometry. Sometimes it was fun. Mostly it was somewhat tedious and slightly boring. But now, hopefully, we'll introduce more excitement in the game. So, so we have a coadjoint orbit. So there is a typical point called eta. So this whole thing is sitting inside inside G star, and we're fixing also some element of the Lie algebra G. So we define the following object, which is called orbital integral. Maybe let me write Ixi of x, and here I would have to say some things that I forgot to say during the last hour. So we take the symplectic form to some power. Conventionally, we divide it by the factorial of the same number, and we write the exponent of at x and the integral over oxi. So here maybe some small remark. So coadjoint orbits are symplectic, and therefore, since you have this non-degenerate skew-symmetric matrix of the symplectic form, the dimension of the coadjoint orbit is always even, and we denote it by 2D. And since omega is non-degenerate, coadjoint orbits are always orientable as manifolds, and omega to the power d, well, over d factorial, but d factorial is just a convention, is a volume form which defines the canonical orientation. So, so that's this volume form or Liouville form that we put in the integral, and we multiply it by the exponential, by this oscillating exponential of the pairing between the point on the orbit and some fixed element of x. Now, of course, a natural question that you may ask me, I don't know whether you are actually asking me on the chat, whether such integrals exist. So that's very much negotiable. So sometimes they exist, sometimes they do not exist. You can ask for which values of x, they are well defined. You can also, you can also, of course, consider x a priori in GC. Remember, we started this with real Lie algebra, so up to now everything was real. But in principle, at this point, who knows, maybe if you go somewhere in the complex domain, maybe the integral will be better defined. So we'll discuss it in examples. For now, we have this abstract notion, as I say, the convergence of those integrals, so the existence of the answer, and the domain of definition for which x is negotiable and should be looked at in particular cases. Okay, so now the orbit method is a principle or idea that certain integral coadjoint orbits, perhaps I will not be discussing in detail what this integrality is, are in correspondence with unitary representations of G. So this is not a theorem, this is a principle. So sometimes it works, sometimes it doesn't work, but we'll not be discussing it in this mini course in such a generality. We'll go down into some more concrete manifestation of that principle. So now suppose rho is a unitary representation. So it's a homomorphism from G to invertible endomorphisms of some vector space. Of course, if it's infinite dimensional, we should also discuss some topology, but for a moment we ignore all of that. And one of the basic features of representations are characters, which is, of course, the trace over V of rho of G. Again, certainly the existence of a character, whether this trace makes sense, very much depends on the representation. It is negotiable. So from this perspective, right, we have two objects which sometimes exist, sometimes they do not exist. Nevertheless, so for us, the manifestation of the orbit method will be the so-called Kirillov character formula. So the Kirillov character formula is a concrete formula relating these two objects. So it says some fixed function that I'll describe in a second, j1 half of x, chi rho of the exponential of x. So this is the Lie exponential, which sends the Lie algebra to the Lie group, is equal to I psi of x. And here, right, at the moment, this formula does not say much. Let me add a little bit more info. For some correspondence between orbits and representations, which will tell you the dictionary between parameters rho and elements psi. So the formula j1 half of x, j1 half is at the moment something which is not yet defined. It will appear on the lower blackboard in some seconds, times the character chi rho of exponential of x. Exponential of x is a group element which corresponds under the exponential map to the Lie algebra element small x, is equal to the orbital integral I psi of x. So that's the Kirillov character formula. So it suggests that there is some correspondence between the orbits and the representations. So that's the first thing. And now j1 half of x is a square root of the function j of x, and the function j of x, the function that probably many of you have seen. For those of you who haven't seen it, it's going to be somewhat surprising. So this is a very concrete function. It doesn't depend on rho. It doesn't depend on psi. It's a function which is defined once and for all. It only depends on x. And this is the determinant of this funny operator, exponential of adjoint x minus 1 divided by adjoint x. You may wonder how does it work. Typically, adjoint x has a kernel, so its inverse is not well defined. But you know, the analytic function e to the s minus 1 divided by s, it actually starts with 1, and then it has some convergent Taylor expansion. So actually, this is an analytic function which is regular at 0. So in fact, here there is no problem with the standard functional calculus to define such a function of the operator adjoint x. So then it gives you an operator acting on the Lie algebra G, and then if at least if G is finite dimensional, as in all the cases we saw before, we would compute its determinant without much of a problem. So of course the square root may be defined only for x small, but in any event, right, where this formula, where the things exist, where this formula is applicable, so that's a negotiable question. So again, this formula, this is a very concrete formula, but it's not a theorem. It's a principle that you need to verify in your concrete case. So there are, of course, the motivation is there are some big subcases, some big classes of Lie algebras for which this formula holds. But you cannot say that this formula holds in all cases, simply because many of the things would not exist. It's likely that the integrals would not exist. It's possible that traces of representation operators would not exist. All right, so let me show you the two examples we saw before. Wow. So the examples of how the Kirov formula works. So the first example, as before, I take G equal to SU2, and for G equal to SU2, we famously have E-reps of dimensions. Let me denote the dimension by m plus 1. So my parameters will be m, and m may be 0, 1, 2, and so on, right? G has E-reps in all dimensions. And the corresponding character, if I compute it on the unitary 2x2 matrix, Z0, 0, Z minus 1, where Z is some unitary number, exponential I theta, right? So this is Zm plus Z m minus 2 plus so on, until Z to the power minus m, right? So that's the standard expression for the character. I can also, of course, now sum up this geometric series to obtain this formula. So sometimes for the future, for us, it would be nice to have expressions in terms of Z, or I can also substitute Z equal to exponential of I theta, and here I will have sine m plus 1 theta divided by sine theta. So that's an instance of the wide character formula in the case of SU2. Now, what about the orbital integral? So the orbital, so that's the character. Now the orbital integral is integral over S 2r. Here, omega will be in degree 1 because d is equal to 1. The dimension of the sphere is 2. 2 divided by 2 is 1. And here it will be exponential. And I write here z, say z times theta. And here my choice of x is I theta 0, 0 minus theta. So that's my expression. Well, remember I have this expression dz dash d phi of the two forms, and this makes the computation of the integral very simple, because now what is the integral over s to r? So z goes from minus r to r, and phi goes over the circle from 0 to 2 pi. So this gives us 2 pi, and here it will be exponential I r theta minus I minus r theta divided by I theta, or this is 4 pi sine r theta divided by theta. Finally, I'll give you the answer for the j function. So you can easily compute it yourself for these x. So the j of x function is equal to sine theta over theta squared, and so j1/2 of x is sine theta over theta. So the curve of character formula reads so sine theta over theta times sine m plus 1 theta over sine theta is equal to 4 pi sine r theta over theta. Now there are two consequences from this formula. So the first consequence, we establish the representation orbit correspondence, which is r equal to m plus 1. And the second consequence, your speaker was not careful enough to figure out how the factors match. Obviously, there should be, in the correct calculation, there should be no discrepancy in factors. And maybe the experts can say what one should do with this 4 pi. For now, let's work in the system where 4 pi is 1. And this would make the, but of course, the Curie formula must work. So that's the first example. As you see, we do establish some representation orbit correspondence, and in fact, the Curie formula gives you this representation orbit correspondence for all semi-simple Lie groups. So this one, in this case, this is an instance of rho, which is the half sum of positive roots. So you should take the orbit which passes through the highest weight of your representation, which is now m. So that you can easily see here. So m is the highest weight of your SU2 representation, and you should add to it the half sum of positive roots. So this will be a point through which your coadjoint orbit passes that you should fit into the Curie of character formula. So let me Let me write down the similar formulas for one. So there are many types of unitary SL2R representations. And so I'll write the formula only for one type. Only for one type of those representations, which are so the reps that we consider will be so-called Fermi modules of highest weight, which is a negative integer. Let me call it minus n. So in this case, let me directly write the character. It's given by a very similar formula. So a character for maybe I would prefer to write it on those elliptic elements. And z, as before, will be exponential of I theta. So this character will be z minus n plus z minus n minus 2 plus so on. So now it's an infinite dimensional representation. So the formula is very similar to what we had before. We start with the highest weight, we descend by the step of 2, but the only difference is that now we never stop. So this is also called the discrete series representation. Now, for our purposes, what is important is not the representation itself, is a character. And the character is now z to the power minus n over 1 minus z to the power minus 2, right? Or we can say it's z to the power minus n minus 1 over z minus 1. And already here, you see there is a little bit of a problem. So now the series that I wrote is strictly speaking not absolutely convergent. It would have been better if the absolute value of z were slightly bigger than 1, right? So then I would have had absolute convergence. So if I tweak a little bit with my things, then this will be truly well defined. Now, of course, putting, for instance, z equal 1 is highly problematic here. And even having z on the unit circle, I mean, then it depends a little bit on the conventions of how I sum it up. Now, let me still write it in terms of theta. So it's exponential minus I n minus 1 theta over 2I sine theta. J1/2 doesn't change. It's still sine theta over theta. Now let's experiment. Let's look at the orbital integral. Now, of course, I should say what coadjoint orbit I have in mind. And the coadjoint orbit, which is suitable, would be this coadjoint orbit, remember. So this corresponds to the case of c smaller than 0. And let me denote this point minus r. So that's the point on the z-axis. So recall two spheres that we were looking at, they were extended from minus r to plus r. But now we are looking at those hyperboloid, down there, which starts at the point minus r on the z-axis. So So here is my integral, right? Remember our great tool. So this two form dz dash d phi. I'm integrating over the orbit of minus r, and here I should integrate again the same thing. It is exponential of I z theta. So that's my orbital integral. Now let me write the formal answer for that integral. It is 2 pi exponential minus I r theta over I theta. And here, of course, right? It would have been better if there were in theta probably some small positive imaginary or negative imaginary. It would have been better if the exponential was really decreasing when I go down. So z large negative, we would like to have this exponential to fall. So in principle, this answer is a kind of conditional answer. That's what we were discussing for those integrals. Nevertheless, if we accept those answers, then we get again up to which is off by so carry the formula, which is again off by 4 pi, but never mind. So exponential minus I and minus 1 theta over 2I sine theta cancels, and this is equal to pi minus I of theta over 2I theta. So as I say, my factors of 4 pi are wrong, but we have r is equal to we have r, which is equal to n minus 1, and that's still the same shift by 1 that we saw before. Now, of course, we inverted everything. We added the minus sign to the point of the orbit, so minus r is minus n plus 1. So that's the same plus 1 as we saw in the previous picture. Right. So that's a brief intro into the representation orbit correspondence and some very simple-minded examples of how it may work. And you see, I would like to finish this hour with one more topic that certainly we'll discuss only briefly. That's a big topic that would have made a mini course on its own, and this is called localization. So remember, we have geometry, we have algebra, and we have a tool which is called localization. So I would like to introduce this tool, and of course on Friday we'll discuss it in more detail. There we'll be dealing with an infinite dimensional example. So localization, it's a big theorem, but I will introduce only some very restricted instance of it. So I'm looking at the situation where M omega is a compact symplectic manifold. Notice that already some of our examples, like coadjoint orbits of SL2R, they don't quite fit into it, but never mind. And S1 acts like Hamiltonian action. So what does it mean? This means that if you take a fundamental vector field for that action, V, then the contraction of this vector field with the symplectic form is exact. And H is a real value function of M, or sometimes it's called the generator or Hamiltonian of that S1 action. So then in this context, so this is actually a definition of Hamiltonian actions of groups. Here I applied to S1, but in general you can do it for other groups. And this is a very, very successful definition. So this definition gives rise to many beautiful consequences. We will now very briefly discuss two of them. So one of them is called symplectic reduction. And here the situation is as follows. So consider the level set of H for some number A. And consider its quotient by the circle action. So in fact, this equation secretly implies that the level set will be invariant under the action of the circle. So it does make sense to restrict the action to the level set. And under favorable circumstances, the quotients will be manifolds. Sometimes they are not, but sometimes they are. Suppose it's a manifold. And let's denote this projection by phi A. And also let's embed the level set back to M. Let's denote this map by IA. So then the claim is that MA is symplectic, and its symplectic form is uniquely defined by this equation, that the pullback of the two form of M to the level set is a pullback of something which is actually turns out to be symplectic from the space MA, which is sometimes called the quotient space or symplectic quotient space, back to the level set. So that's one big construction, right? So there are like many books written about this construction and how it works. But for us at the moment, we are only happy just to look at it like that. And I would introduce one more aspect of this construction. Let me consider the integral. Let me again denote it I of some parameter C. And this will be an integral over M over the same type of expression, omega to the D over D factorial. So that reminds us what we were doing before. And here, well, I can add an imaginary unit, but maybe let me do without imaginary unit for a moment. I take an exponential of T times H. So I consider such an integral over the manifold. And the first remark is, you know, how it works. Let me try to picture it. So that's my manifold, right? So that's the real axis. Here there is a point A. So that's H minus 1 of A. The circle acts on it. And if you quotient by the circle, then you get the reduced space. Now, let me try to use some kind of Fubini integration. So I want to represent this integral as an integral over this real axis. Well, then what will happen? First of all, you should integrate out over the circle. The length of the circle is 2 pi. So there will be 2 pi coming from the integrals over the circle. And then you will have the quotient space, right, over the circle. So on this quotient space, you again have a symplectic form. So it turns out that what we have here, the base will be the volume with respect to this symplectic form of NA. And of course, this exponential will give rise to exponential in T8. So this integral, you can define it, and it turns out that it encodes in some way the volumes of the quotient space. Okay, fine. So now, as I said, that was the first remark. The second remark is exactly the localization formula. Probably, unfortunately, I suspect all of you have seen it already. That's really bad because I've probably seen it for the first time. That might be amazing, but yeah, what to do? So they assume that the fixed point set of the S1 action is finite. This applies to all our examples, and it will be enough for us. But of course, there are more general formulas, and then the formula says that I of t is equal to 2 phi over t to the power z times the sum over those fixed points. And here exponential of t times h computed at the fixed point. And here let me write something slightly cryptic, a function of some operator, which I will now describe. So I would say, together with the theorem that coadjoint orbits are symplectic and the Kirillov character formula, this formula is one of the huge highlights of today's lecture. So let me just explain the notation and give a couple of examples and to finish for today at that point. So what is this? So I think we understand everything in this formula. So that's the sum over the fixed point set. These are the values of the function h at the points of the fixed point set. This is just some inverse power of t. So we don't understand this guy, right? So S1 acts on M, and if P is a fixed point, S1 also acts on the tangent space at that fixed point. But then if you take a vector field, the generating vector field of the S1 action, it will act as an operator. So in an appropriate basis, this operator will look as follows. It will have 2 by 2 blocks of that form. There's skew symmetric, and the entries are integers, which are non-zero. They can be positive or negative, but you can always choose a basis which will be like this. So it will be 2 by 2 blocks. So in particular, those ends, they are called the weights of the S1 action. On CP of M. So what is this phi-fed? Recall that phi-fed is some kind of square root of the determinant, right? And here the determinant, we know what it is, right? The determinant of this block is n1 squared. So the total determinant is n1 squared times n2 squared, and so on. So the phi-fed is actually the product of all those weights. So in total, there are d weights. And of course, you can ask, but how to correctly choose the sign, right? So that's a little bit tricky question. In fact, the signs of ends are not completely well defined because you can always exchange the two elements of the basis. And this would actually change the orientation of this basis. So now you're only interested in the overall sign. And so you are interested in the product of overall orientation of those two-dimensional spaces. This means in the orientation of the whole thing, right? And you want this orientation to be equal to orientation of M, which, as we discussed, is canonically defined by the symplectic form. So this actually tells you how to choose the sign. Right. So this is a very, very beautiful formula, but how does it fit in our story? It fits in our story because suppose you have an S1 which is sitting in your group, right? So then remember, we have this formula for symplectic forms on coadjoint orbits, right? The moment map formula. Now, for this S1 corresponds some particular generator. Let's say X in G is a generator of that S1. So then put H equal eta X. And this puts you in business for that formula, right? So therefore the localization formula applies, the volume formula applies, and so all what I wrote for you, this extract from the Hamiltonian geometry from the moment maps theory, it all applies. So let me use the last 5 minutes just to check how it works in the case of a two-sphere and in the case of the orbit O minus R. So we finished with these two examples. So G is SU2 and M is S2R. Of course, we should still say what is the S1 action. And we consider part of SU2, which is just a rotation around the Z axis. Famously, there are two fixed points, the North Pole and the South Pole, and the localization formula reads I of t is equal to 2 pi over t to the power 1. Now, there will be a contribution of the North Pole. The Hamiltonian function h is equal to z, so we have tz. Now, of course, we need to know what is this rotation number. It turns out that at the North Pole, it's equal to +1. At the South Pole, it is equal to -1. And we get 2 pi, or maybe we write 4 pi, hyperbolic sign of CR divided by t. Or if we put t equal to I theta, and you know, I don't need to, like this t can be an arbitrary complex number. I will recover the answers that I was getting before. So that's the first textbook application. It might be slightly more interesting to look at O minus R. So G is SL2R, M is O minus R, S1 is the rotation group inside SL2R. In our picture, it's still a rotation around the z-axis. Now, I don't quite know how do you call it. Is it a North Pole or the South Pole? Well, let's provisionally call it North Prime Pole. And so I of t is equal to 2 pi over t, again to the power 1. Now there is only one fixed point, this n prime pole. So here we get minus exponential minus tr. And this is divided by plus 1 as before at the North Pole. So we are getting 2 pi exponential minus tr over r and over t. Sorry. And of course, if you replace c by I theta, we get 2 pi minus I or theta over I theta, the answer that we were getting before. Now that strictly speaking, our theorem does not apply, right? So O minus R, simple as it is. So this gadget is absolutely not compact. However, if we check the integral with real t that I defined, if t is positive, it actually exists. It's very well convergent, and it is actually equal to the answer. Maybe we can say that this is. We can also say that this is some kind of formal, localized integral. So this expression, the right-hand side of the localization formula, it exists. It's well defined. The question is whether the integral itself is well defined and whether it is equal to the right-hand side. For some values of t, certainly it is well defined and there is an equality. For other values of t, the integral on the left-hand side does not make sense, and then of course it's not equal to the right-hand side. And we'll see such questions, we'll see such issues on Friday in the infinite dimensional setting. Well, thank you for your attention today. I fear it was already too long. I'm probably over time. So thanks a lot, and that's it for me for today. We'll return in the late afternoon with the mini course of Marcus Mourinho. Again, it's a bit awkward. I should ask whether there are questions on the chat. So kind of everybody understood everything. Nobody understood. But on Friday, I promise, I think it will be material which is somewhat less standard. Today, we did really some grand classical stuff. But of course, probably all of you have already heard it many times.
The answer from Nikita was yes, but our memory is extremely poor.
Okay. Yeah, camera. Camera. Okay, well, thank you. And
Nikita's going to ask one question.
yeah, camera. Yes. Okay, okay. And
how precise, how can precise we can make this? The passage from, character, localization, everything, because it says format localizing.
yeah, I mean, this, if we know that if here, for instance, T has enough of positive real part, then certainly this is just an equality, right? And this basic, okay, you can do the following technically. You can probably cut that space at some level down there and prepare a family of compact symplectic spaces, which would actually have another fixed point. And in the limit, the contribution of that other fixed point would die. That I can easily imagine that's very easy to do, for instance. So for some.
I'm asking whether this is actual proof.
Oh yes, sure. For each of the cut spaces, simply the localization formula would hold true, and then you would see that if you go down, the south pole goes down, then those contributions would die arbitrarily fast. And you can easily write an estimate, which whatever, this is an exponential factor, which would simply die. And of course, on the other hand, the integral over this non-compact space, anyways, it is some kind of improper integral. And here, this would be your definition that you have some cut, and then you send that cut to infinity. So from that perspective, of course, you can make it very, very clear on the analytic side. But of course, next time we'll be dealing with some objects which are more complicated. So there I'm less sure. We'll rediscuss it in 2 days from now. Nikita is ready?
Yeah, so Nikita, can the existence or non-existence of IT depending on T be interpreted as some sort of Stokes phenomenon, perhaps? And I identify certain rules in the T space which separate regions where it exists and where it doesn't. And on regions where it does not exist, is there a reasonable candidate I prime of T to replace it with?
Maybe right. You're probably right. I think yes, probably. Then the idea would be that you should look at the complexified space, right? So now we have some real stuff. And we go to the complexified space, and on that complexified space, we consider what is called Lefschetz symbols. So once the parameter got the wrong sign, your integral diverges, but you're saying that there is another real cycle on which the integral would be convergent, and you would have to compute the integral over that real cycle. So, and that would be related, and that would be some kind of wall crossing, which may otherwise come from the Stokes phenomenon, but here it would come from the geometry of Lefschetz symbols. I think, and that's of course how people, I think also in mirror symmetry or in other higher topics, they also view the wall crossing sometimes. Okay, well, thanks a lot. Yeah, let's stop here. Thank you.